Estamos esperando la señal, no se me desesperen, por favor. Nosotros estamos listos, estamos esperando la señal. Listo, gracias. Buen día a todos ustedes. De nueva cuenta, les decimos que nos complace darles la bienvenida en este recinto, en el tercer día del simposio sobre situación actual y desafíos de la fiebre manchada por Rickettsia rickettsii en México. Estamos por tercer día muy felices de que se mantengan con nosotros para compartirles las conferencias magistrales de especialistas de México y de Estados Unidos de América, quienes con su experiencia nos darán a conocer en este último día del simposio los avances de investigación relacionados con la prevención primaria y con énfasis en el potencial desarrollo de una vacuna canina y el control epidemiológico de la fiebre manchada por Rickettsia rickettsii. Al finalizar esta tercera y última jornada, se va a integrar, como los días previos, un panel experto para analizar los puntos relevantes de las conferencias del día, extraer recomendaciones técnicas e identificar las perspectivas en común. La jornada estará compuesta por 6 conferencias de 30 a 40 minutos cada una. Aproximadamente a las 12 del mediodía va a entrar una videoconferencia para retomar una que el día de ayer, por los asuntos relacionados con la contingencia de Guerrero, no pudo impartirse. Nuestro conferencista sumará las 2 conferencias en una sola. Con este plan pensamos que podemos concluir como el día de ayer a tiempo, a las 18 horas, teniendo 2 intermedios probablemente tan breves como el día de ayer. Y esperamos que nos aguanten un poquito, que corran con el tiempo como nosotros. Ustedes saben que el idioma oficial de este simposio es el español, pero nuestros conferencistas podrán hacer su exposición en inglés, en cuyo caso se hará la traducción excelente, simultánea, por Maya. Y además ustedes van a poder, como los días previos, enviar sus preguntas escaneando el código QR que ya pueden ver en pantalla. Si hubiera tiempo, también vamos a abrir el micrófono para recibir 1 o 2 preguntas del auditorio que nos acompaña en este recinto. Nuevamente a todo el personal de salud del Laboratorio Estatal de Salud Pública, que es personal de salud, a todos los estudiantes, a todos los investigadores que nos acompañan, todos los operativos del Sistema Estatal de Salud. Muchas gracias por permanecer con nosotros. Es verdaderamente importante que lo hagan. De manera que queremos también que se sientan todos bienvenidos aquí con nosotros y que disfruten esta última jornada. Para reiniciar las actividades, me voy a permitir presentar al doctor Roman Ganta. Lo dije bien. El doctor pues nos va a compartir su presentación, ya ustedes la están viendo en pantalla, para decirnos cuán factible es el desarrollo de una vacuna contra Rickettsia rickettsii. Vamos a disfrutar juntos esta presentación e invitamos a pasar al estrado al doctor Ganta. El profesor Roman Ganta tiene un activo programa de investigación reconocido internacionalmente sobre enfermedades ricketsiales que afectan la salud de los alimentos, los animales de compañía y los seres humanos. Su principal investigación se centra en las enfermedades ricketsiales transmitidas por garrapatas causadas por patógenos de los géneros Rickettsia y Anaplasma. Además, ha trabajado mucho con Rickettsia rickettsii. Sus estudios implican la evaluación de la estructura molecular del patógeno, evaluación de la respuesta del huésped, efectos del vector y los entornos de la célula huésped sobre cambios en la expresión del gen patógeno en apoyo del ciclo de vida, la patogénesis, la mutagénesis, la regulación genética y el desarrollo de pruebas de diagnóstico molecular y el desarrollo de vacunas contra varias enfermedades importantes por ricketsiosis. Actualmente, el profesor Ganta realiza investigaciones activas sobre vacunas centradas en la fiebre manchada por Rickettsia rickettsii contra varias especies patógenas de Rickettsia y también de Anaplasma, con el apoyo principalmente de los Institutos Nacionales de Salud, los NIH de los Estados Unidos. A lo largo de los años, el doctor Ganta también trabajó con otros patógenos transmitidos por vectores animales y humanos, incluyendo el parásito de la malaria humana transmitido por mosquitos, el Plasmodium falciparum. Los parásitos también de la babesiosis bovina, transmitidos por garrapatas, como Babesia bigémina y Babesia bovis. También ha investigado sobre la fasciola hepática, que es, como ustedes saben, un tremátodo hepático de la oveja que se transmite por caracoles. El doctor Ganta es autor de casi 100 publicaciones científicas revisadas por pares y varios capítulos de libros. Ha realizado más de 100 presentaciones como orador en diversas instituciones académicas y en reuniones científicas. Forma parte de varios prestigiosos paneles científicos de revisión de pares en los Estados Unidos y en el extranjero. Formó parte de los consejos ejecutivos de 2 sociedades científicas y también es parte de los consejos editoriales de varias revistas científicas revisadas por pares. Tiene 7 patentes y varias solicitudes de patentes más ya han sido presentadas. Le damos la más cordial de las bienvenidas al profesor Roman Ganta.
Thank you. I heartfully felt that I learned Spanish. Unfortunately, I didn't learn Spanish. That is one of the disappointing things I did in my life, I think. I do speak 3 languages, but Spanish I should add to the bucket list. The title, I think Gerardo picked up the title. How feasible is the development of a canine vaccine? The answer is yes. That's what I'm going to share today. But before I go into all those details, I will share about myself, because I see when I'm here the last couple of days, people love to talk, people love to be sharing about things, and the time is a different scale here, which I really like it. My culture is very similar in many ways. I think you will understand. If you let me here, probably I'll be talking till 12, but I don't want to do that. I will cut quickly and soon. Before I go any further, I just want to tell half of the work that I'm presenting today was done at Kansas State University, which was published in 2019 in Infection Immunity Journal. The other portion of the work that I'm going to talk is still hot off the press. My postdoc and other members of the team are still packaging all the data together for compiling it. And it was done at my new home, which is University of Missouri, which that's the symbol, the tiger is the symbol. So we switched from wildcats to the tigers. Well, like I said, I would like to start the journey about myself and my philosophy and what my roots are and what we believe and what all we have been talking about in the last couple of days. This is a Sanskrit statement. Sarve jana sukhino bhavantu. What that means, sarve jana means everyone and every species on earth and everything in the universe. Sukhino means to be peaceful and harmonious. This is the prayer every Indian knows, and end of every meeting this was spelled out before closing the session. So the One Health concept has been already talked about for thousands of years in all the cultures, ancient cultures. Now we are bringing that back, but here is a simple way I can tell. If I'm a great swimmer and I can swim in any place, but if there are heavy rip currents in an ocean or in a water which is so powerful, even my great swim is not going to be any good. So that means your universe should be good for us to be good. So for that, we have to be good. We have to contribute for the good of the universe. That is the One Health concept, which I thought it's interesting that I will discuss that. Well, there is another thing that we always talk about is universe. We have a huge universe around us, which doesn't just stop in this world, but far beyond, stars and all kinds of universes that you can think about. But we also believe there is universe within us. That universe is as big as universe outside, which is like starting from atom to the full body. How we keep all those in very balance, it's really amazing fact. But that definitely requires the universe around us to be strong and good. That is the One Health that I wish Janet is here to listen today. Well, speaking of the universe, my universe revolves around my beautiful lady, Suhasini. And we are married in very close to late 1986 and finished my PhD. I thought maybe it's time for me to get some kind of real exposure to the real places. America is the place we thought will come. We landed here in 1987, this part of the world. When we landed, the plan was that I will be there for 3 years, go back and enjoy my family, contribute to my country, and do all that. Unfortunately, times those days, 35 years ago, in India is not as good as it is today. Today is like the 5th economy in the world, which I'm impressed. But 35 years ago was not the story. So the positive thing is that things can change very quickly in our times. So which is the great thing. So what did Roman do? First thing, we raised a beautiful family. We have 3 children, and we inherited another son-in-law. So they're all doing well. They're the only primary focus I would like to share. My father told, if you do well, I was hoping that all the students are here to share that story. He was a rural farmer back home in India, very remote place. I was the number 7 of 8 children. And he said, if you're a farmer, definitely you contribute for the good of the people. But if you get education, you can contribute way beyond. And your education has a purpose. Not for getting the degrees, not for getting the paychecks. Those are important. But you have to be contributing to the society around you. That is the only way you will be good in the communities and the societies, and the whole world will be good. So I am one of those believers. The time comes, there won't be no boundaries between the countries. There won't be any battlefields. There won't be any borders. Everything will be one big place for the world to go, do whatever they want. That is the dream world I'm hoping for. Probably I may not see it in my lifetime, but it's not far. Well, obviously I did not come here to raise my family. Like my father said, what good I should do, I should definitely contribute for the good of the society. How did I do that? First, like I said, I thought I head back and return to my country and work on vector-borne diseases. Why vector-borne diseases? Vector-borne diseases, we know. Today, we are talking a big thing about Rocky Mountain spotted fever, but we all know that they have so much impact throughout the world, changed the way the histories were modified, the countries' boundaries were changed, lives, how many people survived, how many people extended, which community stayed, which community is gone, everything is all impacted by these vector-borne diseases. I was one of those affected by the vector-borne disease called malaria. I think in the introduction she mentioned. My passion was to work on vector-borne disease, especially malaria. I thought I will come up with a solution for that. I did work. After I completed my postdoctoral training at Scripps Clinic, Research Foundation, California, I went to University of Florida and I worked, but I was not successful. From ticks. Before I talk, I thought, let me talk a little more about India and Mexico. India and Mexico are in pretty much same parallel lines. When we were small children, we used to say, if you poke a hole on the ground, keep digging, you will end up in US. That's what we used to talk. I was wrong. I think we would have ended up in Mexico. Fine, then we would have been confused. How come? People seem to have the same similarities. Geoclimate is same, and biodiversity is very similar. Definitely cultural and family values are very similar here. I mean, I do see a lot of people, you all look very much like Indians, parts of North India and other parts. I can't tell the difference. Probably Columbus start digging the hole from India, end up here, or he tries to dig a hole from this side to that side. He may have the same confusion as he had before. He ended up at the wrong place, wrong India. Well, anyway, obviously, what is more is what we do has to be impactful. I have been working on various tick-borne diseases, which are all over the world. So my contributions, I know, will be impactful. That's why I was happy to be in that kind of a path that I chose. We talk a lot, and this is an eye-opening thing. This is the video. There is a video link there. It's changed its color. You may not be able to read very well, but if you go Google it, NASA has this video. It tells over almost 200 years how the climate has been changing, anomaly of how temperature is fluctuating. And I think Janet, one of you talked, I forgot, that when you increase the temperature of the environment, the ticks tend to go more to the people. I thought that's interesting. So we are talking about global warming. We're also talking about wildlife expansion. We are talking about the tick expansions. We're talking about, here is the publication a few years ago by a group, Dan Sonnenschein is one of the tick scientists, talks about how the amblyomma maculatum expanded. Similarly, other ticks have been very well expanded in not only in the US, many parts of the world. Will that explain? Probably yes. So we are definitely impacting the world. And other demographics, we are deforesting and we are changing the way the wildlife lives. There are a lot of things that are impacting the communities around us, which we are paying for that. We feel bad, we feel sad to see all those heartbroken lives lost, children especially. But we have to work beyond what we think, what we want to work. Well, like I said, I have been working since 1990s, the earliest I started working on tick-borne diseases. But I have been working mostly on Anaplasma and Rickettsia family pathogens since 1994. And there is a one-world concept right here in this group of organisms. Ehrlichia species, Anaplasma species, these are intraphagosomal bacteria transmitted by the ticks. And Rickettsia, which we have been talking about, I delved into for good reason in 2016. I will tell that. And few things I want you to pay attention here. Not all else is same. What we see outwardly is not necessarily same as inwardly. What I mean by that, if you take all the Ehrlichia species, but not the same. Why? Ehrlichia scheffiensis causes macrophage infections. Ruminantium causes vascular endothelium. Anaplasma, granulocytes, marginal erythrocytes. Those are still anaplasma species. Interesting that we are interested in coming up with a solution, right? So we need to understand the biology, which I will explain why it is important. One immediate thing I want to say is here in this slide. Ehrlichia ruminantium is a ruminant pathogen, infects vascular endothelium. And there were publications which say that inactivated whole cell-based antigen vaccine is protective against infections. We tested the same kind of thing with Ehrlichia canis. Ehrlichia species, I thought it should be protective, right? And on that basis, guess what? It was not at all protective. I was thinking it's not the organism, it's not the genus and species that we always associate. Genes, all the genes were so close to each other, so it has to be the same. It's not. Those host associations can make a substantial difference. And today, Rickettsia is also vascular endothelium trophic pathogen. I reasoned that if it's not the genus and species that matters, but perhaps the host cell association matters. So using that scientific logic, we tested this vaccine very similar to Ehrlichia ruminantium. And the long story short, which I will share the data today, it does work very well in protecting. So I'm always a believer of no quick fix for anything. You know, you can't put a Band-Aid on, put a little bit of antibiotic cream and say the problem is solved, because you have to go into the system and find out what causes that infection, what causes that disease, why is it important as a doctors, future doctors, find out the root cause for the reason. Then solution is easy, because then you know what is the right kind of treatment you have to offer. So that is the philosophy I always have been bridging for my research focus. Building the bridge from basic research to translational application. So we started our research, and for that, I can also be open to tell you that I'm not fully trained with all these other different disciplines. But that didn't stop me from working in all these different disciplines, because there are a lot of talented people around us with whom we can climb on. If I want to reach the first floor, I have 3 options. 1, get a rope and go. 2, there is a ladder, you take it. 3, there is an elevator that I can take. I don't have to build
un elevador. Yo no tengo que construir una escalera, y por eso tienes que depender de los recursos que tienes a tu alrededor. Mi primer beca fue inmunidad, entender la inmunidad. Y tenía muy poquito entrenamiento, entonces lo que hice fue que busqué a científicos que tenían el talento, lo invité a que fuera parte, así es que fue mi escalera, entre las dos subimos. Si quieres estar en una escalera, asegúrate que haya también alguien enfrente de ti. Trabaja con él, trabaja con él y ayúdense entre ustedes. Y luego, él también dijo, si quieres resolver el problema, no te enfoques solamente en una cosa, lavar las garrapatas, el huésped, y cómo hacemos todo esto. Preguntar cómo podemos a los demás, cómo podemos solucionar el problema. Es la misma acción en todos los problemas, entonces hay que entender las bases fundamentales para poder desarrollar las vacunas y aplicarlas. Entonces estamos hablando de desarrollar vacunas y aplicarlas. Hemos tenido buenos resultados en las investigaciones y diferentes enfoques. Entonces, estos fueron los fondos para 3 programas diferentes. Y tenemos otros proyectos, ¿no? Vamos a cambiar a la fiebre manchada de las montañas rocallosas. Fue probable que hubiera varias especies. La garrapata del perro café ya estaba en el cuadro y también encontramos otras y estas son algunas de las que mencioné. Entonces los patógenos también se han adaptado a estos factores y están causando la enfermedad. Ha surgido y ha sido un problema de salud pública y emergente en México. Entonces tenemos que encontrar una solución. Como les decía, yo tengo una filosofía diferente. Tengo que hacer algo que contribuya a las comunidades. Si yo lo puedo hacer, si no lo puedo hacer yo, entonces a mí me encantaría pasarle la antorcha a alguien más que sí lo puede hacer. Entonces me encantaría tener una vacuna, ¿no? Porque ustedes tienen estas infecciones en los Estados Unidos, pero muy poquita gente está infectada por estas, pero aquí hay mucha gente infectada. También está el anaplasma, que afecta al ganado en muchas partes del mundo, y tenemos una vacuna para ellos. También en los estudios que hicimos con el ganado, y eso estamos trabajando en Rickettsia, pero había estas discusiones de que esto verdaderamente mata gente en México, en Baja California, la gente está trabajando. Entonces así es como empecé este proyecto en 2016. Las opciones de tratamiento son limitadas, faltan métodos de prevención y hay enfermedades zoonóticas en diferentes huéspedes vertebrados y garrapatas. Y hay otras enfermedades que también afectan otros patógenos. Entonces hacemos vacunas. ¿Qué hicimos? Hay una buena razón por la que seguí este camino. Entonces probamos 2 vacunas diferentes. Los recombinantes, la razón por la que encontré esta porque había una publicación, porque han usado estos recombinantes antígenos y asegura que hay buenos resultados, pero no han hecho más experimentos. Y luego no quieren trabajar con un ratón, quieren trabajar con un perro. Y entonces yo no creo en animales basados en un ratón, sino en los animales reales. Si quieres una vacuna, la tienes que hacer. Si la queremos para perros, perros. Si la queremos para ganado, para ganado. Aquí escogimos trabajar en el perro y qué impacto tenía. Pero esto te trae retos. Porque esto es para una buena casa que vas a salvar a la gente y a los perros creando esta vacuna. Así que así lo empezamos. La segunda que escogimos era un antígeno bacterial de células completas. Esto parece ser una buena promesa. Esto quiere decir que los humanos vacunados estaban protegidos, pero esto era lo que se suponía. Entonces dije, vamos a empezar con esto, ¿no? Y entonces usamos los antígenos en el perro, los desarrollamos y usamos los perros que son los virus. Y sabemos que esta enfermedad, la fiebre manchada, es muy fuerte en los niños. Entonces vamos a trabajar en una variante de animales. En el segundo experimento escogimos un perro de 8 a 10 meses y hay una gran diferencia con la edad. Entonces la probamos y la primera vacuna no protegió. Después la probamos un mes después y los perros seguían enfermos y los de 6 a 8 meses los tuvimos que matar porque no mejoraron. Por el contrario, cuando los vacunamos con la de Cell de células completas, estaban muy bien. Y tuvieron buenas respuestas. Y esto es lo que hemos publicado en estos periódicos científicos. Esto es lo que hemos observado, los controles de no infección, temperatura normal, y la de wholesale, pero similar a los animales no infectados. Y los de control positivo tuvieron fiebre, edema, letargia, falta de apetito y todo esto. Y la vacuna recombinante tuvieron los mismos efectos de los animales. Estos son los datos que pueden ver. El control de la infección es como fiebres muy altas. Aquí muy similar a los animales infectados. La recombinante los animales vacunados con ellas desarrollan una patología severa, igual que los animales no vacunados. Aquí están sobre no infección y vacunados con protección. Y aquí hay una vacuna con no protección. No infección, vacuna con protección. Este es el pulmón. Es una infección. Y los infectados se ven muy similares. Ligado a la misma historia, ves estos vasos sanguíneos que son grandes.
But here is the summary. This was, by the way, board certified Dr. Rickettsia has done. And once again, I'm not going to do everything, but I'll
De Rickettsia, la vacuna dejó usar las células enteras afectadas de protección y había una diferencia significante en los que estaban vacunados. Son resultados muy prometedores.
Okay, so with that,
Con esa publicación aseguramos de los fondos y entonces extendimos esa investigación. En otras fuentes encontramos financiamiento también, pero para la segunda parte del proyecto en el 21 al 2026 extendimos la investigación. Entonces tiene como metas evaluar los adjuntos y la duración de la protección de la vacuna.
Good enough, right? You want to test how long is the vaccine protection. We want to follow that at least for 1 full year, 12 months. So that is the goal. And the second goal is to evaluate if the vaccine protection is also good for tick-transmitted challenge, because what we have done is an IV infection. That's not the same as what people and animals get. It's a tick transmission. So we expect it to work, but we need to prove that. And the next important point is that can this be protected against different strains of Rickettsia? Because I'm hearing in the last couple of days that Rickettsia strains are somewhat different from here versus what is found in the US. I'm sure it's different in South American countries. So we need to be broadly applicable. But some of the data which do suggest that not so much difference between the strains. So there are also strains which are non-pathogenic ones. Like there is one called Iowa strain. This Iowa strain does not cause a disease. We thought maybe if we have a vaccine against Iowa strain, if it gives a complete protection against infection in the animals, that is the great option to try. So that way we don't have to worry about even vaccine-associated challenges as well. Because the way vaccine is prepared is by inactivating the whole antigens, testing them that there is no more bacteria, viable bacteria left, and then using that. So if we are dealing with a non-pathogenic strain or less virulent strain, at least we should be feeling comfortable to take it to the human levels. So these are all the goals for which we received the funding. In the current work, just in wrapping it up, we tested 3 different adjuvants: montanide, quillia, and aluminum hydroxide. And then we used 5 animals each. And this time we chose 8 to 10-month-old dogs. to test the vaccine. So the vaccine formula is primary, the booster 30 days, and followed by IV infection challenge after 50 days, and all the animals were followed for 40 days. Firstly, there is a huge difference, to my surprise. I was wondering what is happening to this. Animals did develop high fever, despite, as we expected, with the non-vaccinated group, but not in the vaccinated group, which is a great thing. But after about 10 days' time, when we observed almost all the animals in the previous study required euthanasia or something heavy supporting care, in this case, we started to see trend backwards. The animals are beginning to recover. So that means it's not just the pathogen. It's like it was well observed and well documented in children, younger animals, also in the dogs. It's a more severe disease. So we still have to follow that more seriously, but we do see that as an interesting observation in this study. So classical fever was observed, and here are the animals with the positive control. They developed all these rashes. Here is the test is being red, and if you leave, some are even more darker, right, which I did not present here. And then with vaccine, everything is cleared by the same time frame. All the hematological abnormalities were observed only in non-vaccinated animals, while vaccinated animals had very healthy clinical picture when it comes to complete blood analysis. Here are reticulate hemoglobin and drop in hemoglobin and hematocrit and all the parameters that we have seen. Then we looked at these, where else we see this? There is like I mentioned, there is the spike, there is a drop in platelets in all the infected animals, which seems to be restored when we vaccinate. And here is the pathological data. Here is the lung with control versus see this healthy looking following the vaccine. And it's the thymus. There's a lot of edema that was observed again by the pathologist. What I think you can clearly see that. And on the contrary, that vaccinated animals had very healthy looking thymus. And I think it's more obvious in the liver. You can see that lot of infiltration of the cells and the damage, whereas the vaccinated group cleared all those. And one thing I want to point out that these lesions are only observed during the clinical phase of the infection. Here's the measure, how far we can look at the presence of the organism. All these control group animals, we could see them up to first 2 weeks. So there is a small window where you can see the infection even by PCR. And on the contrary, vaccinated, basically you don't see. There is one positive that we have seen in one of those animals from these 3 different adjuvants. So we just want to present the data as is. We don't want to change it. It could be false, it could be true, but it is a data. We have to respect that. So often PCR can be interpreted as maybe just DNA circulating, right? So we wanted to prove that it's not just PCR, it's viable bacteria is what we are seeing. So we collected blood and we put them in culture media and see that all the infected animals, you see the infection is being viable infection recovered in culture. Contrary to that, all these 15 animals, doesn't matter which adjuvant we used, bacteria is completely cleared, which is not even detectable by culture methods. Here is the point I was trying to mention, that these yellow highlighted animals, we sacrificed close to day 14, I believe, to see how the pathology looks like, and for comparison to 3 animals to 3 animals. And all other animals, we left it till 40 days because they recovered the clinical phase of the disease. So the pathological lesions were only observed during the early clinical phase, which is cleared by the vaccination. And if you leave the animals long enough, so the tissue damage is healed with time. That is, doesn't matter whether infection is there or not. So the key is to control the disease early on. And when you bypass that, there is hope on the assumption that we can take it straight translation into humans, but even in the dogs, that is the story. So we do see a spike. Here is the vaccination portion, and then the red line is where we challenged. The vaccine did induce the IgG response. Here is what we're measuring, and here is the infection controls. And then we looked at the different types of IgG isotypes, IgG1 and IgG2. And both IgG1 and IgG2 were made at a higher levels, and the ratio is 1:1 literally for the vaccinated group. On the contrary, the infection controls only produced high levels of one IgG, which is primarily IgG2. So here is the ratio. You can see the difference. So that means the vaccine already created enough strong dose of antibodies in equal levels. And then we looked at other measures like, pro-inflammatory cytokines, and they are down following vaccination. On the contrary, infection seems to be pushing the spike in the cytokine levels. And same is true with, there is a trend for anti-inflammatory cytokines. So the long story short, what we have is that we have an implicating evidence supporting that bacterial whole cell antigen vaccine offers sufficient protection in preventing the disease, severe form of disease, at least in dogs. So where do we take it to next? Like I mentioned, we would like to assess the duration of the immunity and evaluate its protection against tick-transmitted challenges, and the third one is to see whether we can see good protection with heterologous strains, particularly those with non-pathogenic or less virulent strains, which will be an ideal vaccine, in my opinion. And these are the goals for which we already have funding. So we expect to complete this project. But what I really think is more valuable, if there is a possibility working with your communities here, is to perform these field studies where if this vaccine prevents infection spread among dogs and also block the pathogen transmission to ticks. So something I'm open to discuss. I don't have funding for that part. I will still try to explore other sources. Some industry supported. I did try at CDC, but I was not having good luck with that. But if there is a possibility for you all to think that this is the way that we should take this vaccine to the next step, and so that will be a good thing. I think we can contribute for the good for improving the health of RMS of patients and communities and the dogs. So the work was initially done by these two primary in the first publication. His name is Andy Al-Hassan. He's now in Caribbean island as a professor, and he's still with me. And the remaining portion, the current work, was primarily led by this lady. Her name is Pearl Latre de Latte. And here are all the various members of my team. And here are some of my members actively in my project. And with that, I'll be very happy to answer any questions you may have about this research, or about me, or about my science, whatever you have. Thank you.
Thank you so much, Doctor, for your comments. It was very grateful to listen to, and it's very interesting.
Thank you.
We have 3 questions, and if we have some time, the people can ask.
We're in part of the world, time has no boundaries. I'll be happy to talk as long as you want.
All right, thank you. The first one, in your opinion, how could physicians collaborate in the research needed to develop a vaccine for Rocky Mountain spotted fever?
How physicians collaborate? That's an interesting question. We have a couple of physicians here. They may be the better people to address that for me. This vaccine that we are testing is right now on the dogs. But the best way to collaborate for physicians, if they are at least in the US or here, they should be aware that the disease is more, and they should start looking into those cases. And I do hear for a number of people, even in the US. That I can tell you the story, which is eye-opening. Once I had a garage door problem. I called a guy to come and fix it. And he came, and then he's fixing, and I was talking what you do, because I'm one of those, I love to talk. And he said, I work on tick-borne diseases. And then he said, what is that? I said, it's like, a pathogen which can cause infection when I have a tick bite. And some of them are very deadly, like in children. And then I told him, one of my physicians, actually my own physician, he sent a blood sample to my lab to run a test. It turned out to be RMSF positive. And then immediately I told him and he was treated. The child was treated. And at least my garage door was fixed for free. He was so impressed. He said, doctor, you saved my child's life. So there is things that the doctors can still do. And when you see in a patient which is likely to be RMSF, and discussing with a scientist, basic scientist like me, is not a bad idea. Because we're not trained as doctors, but we are knowledgeable enough to contribute, like something very simple as running a PCR assay, or even simply guiding them. If you do see, it means, I know I cross lines here. If I see a patient, or if the doctor tells that this patient has a tick bite, has some serious illness, I did tell my doctor, go ahead and start doxycycline. I'm not a doctor, but please do. This is my recommendation. So, again, sometimes it's an opinion, but opinion matters sometimes. So, yeah.
The next one is, a limiting factor is missing knowledge about immunogenic rickettsial determinants in general, and especially about those that are recognized by T cells. Regarding this, which is the current situation and your working area?
Yeah, good point. We only talk the bottom line when we talk the research. We are checking what are the important memory T cells which are contributing, and how long is the memory. That's another reason we wanted to pursue this research for 1 year, to see how long is this vaccine protection. So all those things are going to be helpful in fine-tuning and improving the vaccine. Yes, we are working on it. We have a collaborator. She's working on those aspects as well.
And the other one is, which is the perspective of including the use of mRNA as an adenoviral vectors, such as the ones using COVID-19 vaccines?
Yeah. mRNA vaccine is basically protein vaccine, but we start with transcript. So the vaccines progressed from whole cell or live vaccines. There are 5 different cocktails. Like DNA, you put that, DNA becomes mRNA, mRNA becomes protein, and the protein is what you intracellularly induce that. In my opinion, at least based on the data that we published, mRNA vaccine will not work, because you may only target 1, 2, or 3 very few proteins, mRNA. So bacterial, again, that's why fundamental basic biology is so important to know. mRNA vaccines work great for a lot of this viral, because their viral genomes are small, and you can pick the ones which are really exposed to. But in this case, that's not the case. So mRNA vaccine may not work for Rocky Mountain spotted fever.
Thank you, Roman. And I loved your talk, and I love the fact that you emphasized how important the multidisciplinary role was. That this is any problem that deserves to be fixed, and especially a huge problem, requires many people. And this problem will require thousands of people. Everybody has a role to play. It's not going to be solved by Dr. Alvarez alone. It's not going to be solved by myself alone or CDC itself. It's everybody has some element to play, and I think you really emphasize that. So thank you for doing that.
Thank you.
I had just a couple questions about the vaccine itself. You challenged the animals 50 days after the they were
About 30 days after the booster.
30 days?
Yeah.
Okay,
But we want to extend that to 4 months, 8 months, 12 months.
okay.
And we want to test. We have done that similar experiments for Ehrlichia, Schefiensis, for example. We got good memory and good protection, but it's a live vaccine there. That's a completely different story here. But I want to see how it is. Suppose we might get protection. We're good, we're lucky. Otherwise, we have to look at plan B. Give a booster at 4 months' time or 8 months, whatever it takes to see it. Yeah, that's definitely in that.
And so which strain did you use?
The most virulent one.
Sheila Smith?
Yes.
So, yeah, Sheila Smith is extraordinarily virulent, and so
Yes.
you would expect it to be similar to
Exactly.
the strains in Mexico. Nonetheless, I think what you're proposing is good in terms.
Yeah.
If you're going to be using this vaccine in Mexico, I think it's imperative that you use a Mexican isolate.
I'm open to
and
get
so-
those isolates into my lab and start
Well, I
doing
think
that.
that's one of the things that we're all talking about,
Right.
trying to accomplish.
Yes.
So I think it's all the more reason
Yes.
to pursue that.
Well, like I said, this is, I'm an Indian, not this part of the world Indian, but real Indian from India, with the philosophy that life is very short for all of us. We believe that life is like a bubble. Who knows when it will pop? But we have to be impactful and contributing. So the vaccine is one of those, I think, translational. I know Dave, Dr. Walker, and me, we talked a couple of days ago. We have a lot of research that goes on in understanding the cellular pathogenesis of, how the cells progress, how the genes are expressed, how proteins are interact. All that is great. All that science, if we don't translate. By the way, Dr. Walker, I consider him as my mentor. He always have been a great mentor in giving the right guidance. I know he's doing that here too, but he has done that to me like many people. And there are people around you to tell you the right path, so which is very helpful. Yeah. Sorry, I distracted you.
No, so one thing that I think is going to be critically important about this vaccine is to prevent acquisition
That's
by
the
naive
last-
ticks
yes, yes.
to pick up.
That's-
But I think it's promising
It is.
that you were unable to isolate the organism. So,
Yeah, organism is completely gone.
Right.
But again, nothing doesn't mean nothing. It may still be.
Right, you need to
So
show
the
it.
proof is in the pudding, right? So you have to put the ticks and see that infection is not acquired. That experiment has to be done. And we will be doing those even part of our following experiments to see if the acquisition is happening in vaccinated and non-vaccinated. That will be still part of my ongoing study. But what is more is to add those field isolates, which are more important for this part of the world. And actually, there's Ted Hackstead published one paper. He compared all the various strains. We cherry-picked 3 strains, Morgan, M, and Iowa, and besides the Sheila Smith. For these studies, the reason for that, I think, based on what he published, he says that not that much difference between all these strains, which is a promising. But what is more is Iowa strain doesn't even cause disease in people. It's not even pathogenic. So we are very looking forward to do those experiments. It does the Iowa strain, give a protection against Sheila Smith and Morgan and M strain, and maybe the Mexican strains that we can see. And so we have an option to do. And unfortunately, this is an expensive project. It's a $3.9 million project that I'm holding to do this. Luckily, thanks to all the reviewers who are willing to give this money. And again, this is one of those very unique projects. It's dear to my heart. These are 2 projects. One of this is this one. And we only have 1 publication with which I was able to get funding, which is really a record for any funding. Yeah, Chris, I'm with you, and maybe Rado will help, and community here will help.
Yeah, we're 100% behind you. And CDC is too, actually. CDC views this as a very high or our group at CDC views it as a very high priority project. And I think working out the details and the complications between the funding persons are what our challenges are. So thank you.
It's fine. So here is the most important thing. If you have a heart to do it, funding agencies doesn't matter. This is what I always tell, and that's what I always did. You want to do something, you can do it. You can find a way to do it. See, additional sources are helpful.
Roman, thank you very much for your wonderful talk and very inspirational, I think, for students. Thank you very much. And I think a sign of your friendship is I'm going to make this announcement, please, as a friend for you. El doctor Ganta está cumpliendo años hoy y está como una muestra de su amistad, está aquí con nosotros. Ofrezcámosle un aplauso de cumpleaños al doctor. Happy birthday, my friend.
Thank you. I thought I would bring my wife for this, but I did not. But I found a huge family here, and so there is no better place to celebrate my very special, sweet 65th birthday.
Thank you, Roman. Thank you.
Thank you.
No, thank you for being here with us. So I think it's this symposium is about building bridges between science and policies. So your results are, to me, very promising. I think it's the future. It's not the immediate future, but I think it's a really a real solution, maybe a potential really good solution for the future. But you as a scientist, what do you need? I mean, you as a scientist, see in Mexico, what do you need to advance in your project? I mean, because of course there's methods and many other things that you need to do, but if you were to the possibility to ask help to us, what do you need to make the next movement, to make the field studies or so? What do you need?
Well, good question. Yeah.
Yeah.
Thank you. Firstly, I think there's no question that this vaccine needs to be tested in a field trials. There is no question that this vaccine needs to be tested, like Chris mentioned. Look at the strains which are circulating in the dogs and use those to see if can we make a vaccine with those, for that matter? Or can we test this Sheila Smith virulent or Lay virulent vaccine to see if it gives the protection, prevention of the pathogen acquisition in the dogs. So those are all the goals which requires, first of all, needing to build bridges, needing to have open collaborations, and find ways to fund those, which requires, of course, will be actively willing to write and work with the teams and still seek the support. And I think Chris is definitely, and the CDC is a very instrumental they have done. I'm very happy to see all the progress. Yesterday, the CDC team presented. The strategies work, approaches work. You have a ways to control, add one more variable to improve the One Health concept. And for that, I'm on standby. There are things that you may have in your mind that I don't know. I think it's best thing is to sit down and discuss and make a plan. And you may have some big administrators here who wants to sit down and say, how do we do it? How do we come up the next level? Are we ready to take the next step? So what is the priority? All these things need to be discussed and in a public forum with everyone. I don't think we can decide that in just 2 minutes. But definitely, what is needed is to establish a collaboration and think of all the bigger picture things that we need to take it to the next level.
Thank you very much, Roman. I have a question more about the money. And, we know it has been very hard to have vaccines out there for neglected diseases. And how you convince the laboratory companies to produce this vaccine?
Oh, that's a good question. Laboratory companies are only after money. Obviously, you can see that. There is a company with whom I'm trying to work with. They expressed interest, but again, these companies go back and forth. There is a marketing analysis team. They tell them, oh, it's a disease, only few reservation areas. It's not important. I did tell them that this is a disease all the way from Canada to the down south America. And so I told them just file, apply, and worry about those things. So they're coming back and forth. If we have more data to tell them, here is the situation. Believe me, I'm sorry to say that it was eye-opening to me that how serious this disease is till I physically came and attended this conference, even if I did not understand most of what was spoken, but still I could see what was there in the slides and what's the feeling and the chemistry and the resonance. So that needs to be carried to these industry partners. You may have some industry partners locally who are willing to do that. And that's because that's where they can make money. It comes down to how much money they make. They don't care they're saving people or not. They're very open. Businessman thinks in dollars. So they see dollars, whether pesos or dollars, it's all the same money. That's all they matter. But I think we need to work on those aspects. We did file patents to discuss those options because that is the only way that you can invite any industry partners.
Thank you.
It's so nice to see all those future doctors and learning about what they are going to face. And I think your passion should be to find solutions. And I'm sure you all do that. Congratulations. Thank you.
Well, Roman, I wanted to thank you so much for the presentation. And I do have two questions for you. One is your data does show that the puppies and those that are 4 to 6 months are clearly very critical in like maintaining this in the environment, right? Your lab studies showed that they get severely ill. What are your plans for also testing the vaccine and the efficacy in those puppies? That's my first question.
We do want to test them because they are not listed as the goals, but goals can change with NIH money. I do plan to have some with younger age and older age and see what happens with even much older. Is there any difference, age-dependent changes? And there is another experiment. We want to do the infection by tick transmission and see what happens with those two. When it comes to tick transmission, that's a real way to test it because ticks are only putting so much of bugs. Doesn't matter younger or older dog. And also they are impacting the host immunity in a differently to promote the infection. We have seen a good difference in Rickettsia, Anaplasma marginale infection. So infection with Anaplasma marginale with tick transmission, I'm writing a manuscript, by the way, it will be very soon there. It's almost 6 to 7-fold, I believe, more bacterial loads, and there's so much difference. So yeah, tick transmission is there, but definitely we're planning to do these experiments with different age group animals to see how the infection and how the vaccine.
Great. And my other question, which is very simple, but maybe very hard to answer, but it seems like it's great to see that you're starting to answer the question of if this is possible, but when? Like when, because I get asked this as well, and just wanting, we won't hold you to it, but.
No, I think when is all subject to experimental, and there are a lot of other things go in when it comes to the regulations. And animal vaccines probably it's less regulated because they are USDA regulated ones. I was with the USDA sometimes. If it is a human, it's a completely different story. Animal vaccine approvals are fairly quicker, but you have to have all the data in hands before you take it to that. For that, we need to work. But again, these regulations may be different in Mexico versus US. So who knows? When it could be as soon as 5 years from today and maybe 10 years. But still, I do see the light at the end of the tunnel. That is the most important thing.
Okay.
Thank you.
We're going to give you a present for your birthday.
I will take that.
Turkey hanger.
Thank you.
And also, we want to thank you
Thank you.
for your beautiful presentation. El Departamento de Medicina y Ciencias de la Salud de la Facultad Interdisciplinaria de Ciencias Biológicas y de la Salud de la Universidad de Sonora le otorga esta constancia al doctor Roman Ganta por impartir la conferencia ¿Cuán factible es el desarrollo de una vacuna canina contra Rickettsia rickettsii? El 9 de noviembre de 2023. Thank you very much.
Thank you so much.
Y vamos a darle nuevamente la bienvenida al doctor David Walker. Porque veo caras nuevas, me voy a permitir leer nuevamente una reseña del doctor David Walker, quien ha recibido premios como alumno distinguido en Estados Unidos, mientras que fue residente de patología, profundizó su compromiso con las enfermedades infecciosas tropicales durante sus 6 meses de estancia en el Instituto Gorgas de Panamá. Posteriormente, en los Centros de Prevención y Control de Enfermedades de los Estados Unidos, inició investigaciones en el laboratorio de nivel de bioseguridad nivel 4 sobre la fiebre de Lassa. Y durante 12 años en la Universidad de Carolina del Norte desarrolló un laboratorio de bioseguridad de nivel 3 en el que estudió muchos casos de fiebre manchada de las montañas rocosas y se estableció como investigador independiente en rickettsiología. En el Departamento de Medicina de la Universidad de Texas, desarrolló programas sobre enfermedades zoonóticas transmitidas por vectores. Además, fundó otros laboratorios de nivel 3 y fue el director fundador del Centro Colaborador de la Organización Mundial de la Salud para Enfermedades Tropicales, así como el Centro de Defensa Biológica y Enfermedades Infecciosas Emergentes. Después de ser líder de diversos proyectos financiados por los Institutos Nacionales de Salud de los Estados Unidos sobre Rickettsia durante 30 años y Rickettsia durante 25, el doctor Walker ha centrado su atención en el tifo del matorral, ocasionado por Orentia Tsutsugamushi, y ha dilucidado el papel de las células T, CD8 en la inmunidad y está buscando la identificación de antígenos protectores para el desarrollo de vacunas contra esta enfermedad, contra el tifus del matorral. Además, está buscando un enfoque práctico para interrumpir el ciclo de crecimiento de la garrapata café del perro. Es miembro de la Sociedad de Enfermedades Infecciosas de los Estados Unidos. También es miembro de la Sociedad Americana de Medicina Tropical e Higiene y de la Academia Americana de Microbiología. Nuevamente le damos la bienvenida al doctor David Walker con nuestro agradecimiento profundo por estar con nosotros.
Can you hear? Yes, now it's working. Buenos días a todos. Yo soy muy feliz de estar aquí otra vez y tener oportunidad de hablar otra vez. Y primeramente yo quiero hacer mis felicitaciones, my congratulations to Roman Ganta por todo el trabajo que ha completado. Este es hecho. Lo que yo voy a decir es un plan que vamos a hacer, pero todavía no hemos hecho. You can see here the two people that are the principal investigators of the grant that we have obtained from the CDC. And I think it is a good plan. I think it's going to advance our knowledge. You have to understand, and Roman understands as well, but he said $3.9 million, I think. The CDC was not able to give us anything near that amount of money. In fact, probably less than a tenth of that amount of money. And so our studies will not be as good as his studies. And that's, but maybe we can build on what we learned. And I think maybe you will like to think about the plan of the research and what it's going to probably accomplish. The two principal investigators of this grant are Maureen LaRoche on the left. She got her PhD, she came from Martinique, island in the Caribbean, which is part of France. And she went to the mainland France and did a PhD, and then came to UTMB as a postdoctoral fellow. And she is a vector biologist. She's very skillful at working with ticks. She does mass spectrometry proteomics, so she's a scientist. And she's the contact of the multiple principal investigator system where these both are principal investigators. And she's a dynamic woman, and she's an assistant professor, so this is really an opportunity for her energy to blossom. The person on the left, Lucas Blanton, es un médico interno, de internal medicine interna, y sabe muy bien medicina. También tiene especialidad en enfermedades infecciosas y es una persona muy inteligente y también muy amable. When you meet him, he is never present. No es orgulloso. Es siempre sabe mucho y puede hacerlo. He came to me after I gave a lecture when he was training to be an infectious disease physician. I gave a lecture about rickettsial diseases. And he came up to me after the lecture. Always when I give the lecture, I think I'm like a priest. I'm preaching to the audience. And I'm going to convert one person to come work in my laboratory and do their life work with me. So, in many years, people will come and spend 1 year and then leave. Lucas came and he's still there. He's now an associate professor. He writes the textbook chapters that I used to be the primary author of in the most famous books of infectious diseases, Mandel, on spotted fever, Rickettsia, and on murine typhus. He works in the laboratory. Most physicians don't work in the scientific laboratory. And he works on very difficult things like opossums and growing Rickettsia in biosafety level 3. And he's very skillful at these things. So he is one of the principal investigators. And I think, if I remember right, the idea of this project was mine. But at this point, I'm a co-investigator and advisor, and these two people have moved on forward with much more detail, and it's really their project. So as we've heard in this meeting already, outbreaks of life-threatening Rocky Mountain spotted fever in humans and dogs associated with canine tick maintenance cycle constitute an important One Health problem and opportunity. So this has been shown very accurately. First I knew about it was in Brazil, but when I went back and read the literature, I realized it had been going on in Mexico many, many, many years ago. And then again. And in Colombia, where I'm now collaborating and training people, and that's the country in which I'm actively involved at present. And as you've heard about the Native American Indian lands in Arizona. So I knew Rocky Mountain spotted fever in North Carolina, and it was a sporadic disease. Yes, it was the state that had the most cases of any of the states in the United States, but it was one case here, one case there, later time another one. However, when you looked at the CDC data, you found that 4% of cases of Rocky Mountain spotted fever occurred in a family in which there was another case. So there were foci where there was transmission to more than one person. But the idea of an outbreak seemed very strange, because usually we think of outbreaks as person-to-person spread. I mean, as a physician who knows some epidemiology, that's what I think of as an outbreak. And Rocky Mountain spotted fever didn't make sense until we came to understand the cycle of brown dog ticks and dogs. So the brown dog tick, Rickettsia sanguineus insulato, acquires the Rickettsia from bacteremic dogs. So that's been proven that it can become infected by feeding on a dog. And it can maintain the Rickettsia transstadially. So if it feeds as a larva and then molts and becomes a nymph, the nymph is infected. And then when that nymph molts and becomes an adult, the adult is infected. If it feeds as a nymph, it becomes infected. And when it molts after a blood meal, the adult is infected. The adult female lays eggs that are infected, transovarial transmission. And there's a lot of conflicting data that I really don't understand that shows that the Rickettsia can be very pathogenic for the tick, and it can reduce lots of its biology, including killing the ticks. There are other studies that show 100% successful transovarian transmission, successfully maintaining the organism in nature. So we know that can happen. I do not understand the discrepancy between those, but that's the way nature is often. It poses to us things that we don't understand, and we have to plan a way to unravel the answer to the problem. So then this adult tick will feed on a dog and transmit it, and that dog is infected. And all the ticks that are on that dog have the opportunity to take a blood meal and become infected. There's also another important mechanism of transmission that we need to consider, and I don't think we have considered it, and that's co-feeding transmission. So one example of co-feeding transmission occurs when two ticks are feeding adjacent to one another. And you've seen the pictures where there are 100 ticks side by side by side. And if there's an infected tick and it injects the Rickettsia, the adjacent tick can imbibe the Rickettsia and become infected. So an uninfected tick can become infected just by feeding beside an infected tick. And that's something I'll come back to at the end. And the transovarial transmission means that the Rickettsia sanguineus can be ambos vector y huésped. And the dog is really an amplifying host. It's not really what I would consider to be a reservoir. So our hypothesis is that vaccination of dogs with Rickettsia amblyommatis stimulates immunity that prevents infection of dogs and prevents acquisition of Rickettsia by Rickettsia sanguineus feeding on vaccinated dogs. Rickettsia amblyommatis is a rickettsia of unknown pathogenicity. It is, there have been places, an example of a place where a study was done is Fort Chaffee, Arkansas, where Ehrlichia chaffeensis was discovered. And soldiers would give some serum before they went into the field. They would go into the field and have military exercises for weeks. They would come out and go back home, and they would draw blood from them and see if they made antibodies. So there were people, some of them seroconverted, made antibodies reactive with Rickettsia rickettsii. But the ticks that are there are Amblyomma americanum. And Amblyomma americanum, it's been occasionally found to have a Rickettsia rickettsii in it, but it's really not a vector, and it's certainly not an important vector of Rickettsia rickettsii. These ticks, more than half of them have this Rickettsia in them, Rickettsia amblyommatis. So it's very likely, since these soldiers that seroconverted actually are making antibodies to Rickettsia amblyommatis. None of these soldiers were diagnosed as having an illness. None of these soldiers were treated. And so whatever they had was subclinical. They went back and asked them very carefully if they had any list of symptoms. And they compared the same question there that was given to people who did not seroconvert. And they found there were some symptoms that they recalled more than the others. So it's possible that they may have had, some of them may have had an undiagnosed illness, probably a mild illness. But this organism is a live organism, and it stimulates antibodies. So we have studied this organism in guinea pigs. And here you can see on the left a fever curve. These are the animals that are infected with let's see. So this is not the study the first study. This is the second study. The first study, this is a vaccination study. The first study, we inoculated guinea pigs, and they continued to gain weight. They showed no signs of illness at all. And then after that, we challenged them with Rickettsia rickettsii. And this is the results of that study. The animals that were immunized, this is before they were challenged, developed a very high antibody titer, reactive with Rickettsia rickettsii. They were injected with Rickettsia amblyommatis, and they made antibodies to Rickettsia amblyommatis, but they also made antibodies to Rickettsia rickettsii. And you can see on 14 days after inoculation, the geometric mean titer was 1 to 724. On 28, it was 1 to 1,825. So they made a huge immune response. It was reactive with Rickettsia rickettsii, and they had no signs of illness at all. They were in a growth phase, and they were gaining weight, just like the animals that were not immunized. So then we challenged the unimmunized animals and immunized animals. And the unimmunized animals developed a fever, and then their fever dropped tremendously and they died. And that's the way you see it. That's what happens to guinea pigs, is they become hypothermic and die. They also lost weight and then died. The other guinea pigs continued to gain weight after they were challenged with the same dose of Rickettsia rickettsii. So it was complete protection and without signs of illness. And it seemed to us that this was really a demonstration that this was a live vaccine that would protect against Rickettsia rickettsii. So this is the planned study for which I hope we have some results to show if we have another meeting in another year. 4 dogs are going to be intradermally injected with Rickettsia amblyommatis, and we're going to observe those dogs for 6 weeks, watching for signs of illness and evaluating their immune response. And then after 6 weeks, we're going to challenge the dogs intravenously with Rickettsia rickettsii. And during the subsequent 4 weeks, we observe the dogs for signs of illness, and we're going to draw blood from them to see if we can detect bacteria, if bacteria are present, what quantity is there, and to measure the immune response. There will be a control group of dogs that are challenged similarly as these with Rickettsia rickettsii intravenously, and we're going to observe them for signs of illness, draw their blood, and evaluate them for the presence of bacteria and quantity of bacteria and their immune response. None of these dogs will die. Roman has amazingly done a study where he could actually evaluate what happens in the end to the dogs. When our dogs lose a certain amount of weight to where death is likely to follow, they will be treated, and none of these animals are going to die. And the animals, at the end of this study, all of the animals will be put up for adoption, and people will take them home and have them as pets. And this is something that may sound like it's a kind idea, but it's also a way to get permission to do this study. We probably wouldn't be allowed to do the study if dogs were going to die. So we're going to measure body temperature, the weight change, the signs of illness, anorexia, lethargy, conjunctivitis, which is very frequently present in dogs that have Rocky Mountain spotted fever. And we're going to draw blood from both the dogs that are naive dogs that are challenged with Rickettsia rickettsii and the immunized dogs. And during the immunization and during the challenge on days 0, 3, 7, 10, 14, 21, and 28. And we're going to do a complete blood count, a comprehensive blood metabolic panel. So you look at things like sodium, potassium, chloride. You make sure that nothing gets out of balance, and the rickettsial load. And we will also measure on days 7, 14, 21, and 28 the IgG-IFA titer, the T-cell immune response to Rickettsia rickettsii as determined by ELISpot assay for the number of T cells producing gamma interferon, interleukin-2, interleukin-4, interleukin-10, and interleukin-17. So then there will be another experiment to determine if we can block transmission to ticks. And so we're going to have a similar immunization of the dogs, challenge of the dog 6 weeks later, have on the dogs feeding 200 naive nymphal stage ticks per dog. And then we will, when they come off, when they drop off, we're going to remove a leg and test it, because if it becomes infected, the hemolymph is infected, the hemolymph goes into the leg. It's a good sample to determine whether the tick got infected or not. And the tick will then remain alive, and we will have it for further study if necessary. And we'll actually, we'll do quantitative PCR on another leg and culture for rickettsia. We would do the same thing with the dogs that are not immunized after they have been infected, and we'll do the same thing of placing ticks on them. When the ticks are replete and drop off, we will evaluate them for infection. Now, We expect that we will get protection without a booster. I think a live infection stimulates the type of immunity that is solid and will not require a booster. Obviously, we haven't done anything, so we're going to find out whether that's true or not. But that's what our hypothesis is. The things that are going to need to be done after this, if this works, will be determine the duration of infection, of protection. Because if a dog is protected for a short period of time, it's not going to serve well in the neighborhood. It needs to actually continue for the life of the dog. Also, will the dogs be protected from infecting ticks by co-feeding? So if this dog's protected, but two ticks get together, feeding at the same site, and one of them is an infected tick and one is not, will co-feeding result in infection, or will the immune response prevent that? You know, there are modelers who take a situation epidemiologically and take a lot of variables and determine a prediction of what the outcome will be. And I believe some modelers need to develop a strategy for immunization. Are we going to immunize all of the puppies as soon as they're born within the first few weeks of life? Are we going to go to some location, a hotspot, and immunize that hotspot and around it? And how far around it? You know, maybe how far the dogs travel, where they take the ticks, may need to be evaluated in the modeling equation. And this should probably determine the strategy of how to distribute the vaccine. And then once a good vaccine is had, and I think, you know, Roman's a lot closer to having a good vaccine than we are, we're going to have to determine how will it be manufactured? How will we produce it? Is it going to take a biosafety level 3 laboratory? Are there companies that manufacture things in biosafety level 3 laboratories? I know that in the United States we have no vaccine for Coxiella burnetii, which is a biosafety level 3 antigen, and whole-killed organisms are protective in Australia. They produce it, but it's not produced in the United States. I don't know why that is, or whether the biosafety level 3 production plays a role in companies' decisions. Then the vaccine must be stabilized. It's going to have to be just as good as you gave it in the experimental laboratory when you take it into the field. Well, how will that be done? Will it require a cold chain? So if I'm using live Rickettsia amblyomyces, how am I going to have to keep this live Rickettsia amblyomyces to go out to some distant place? Or is there a different approach? Can we lyophilize it and reconstitute it in the field? Well, it'll have to be tested. If that's the way it's going to be done, we have to prove that will work. And so you can see that these are a few things. I'm sure that I have not thought of all the things that would be necessary to be done. I was sharing an anecdote about myself. You can tell I'm a very old man. And so I've lived a long time. And I had this in my mind when I was in North Carolina that I was going to make a vaccine for Rocky Mountain spotted fever. How long ago was that? Oh, it was more than 40 years ago. So at one time I was interviewed by a newspaper, and they asked me, well, how long did I think it would be before this vaccine was ready? Oh, I said a couple of years. I'm a lot wiser now than I was then, okay? And I still don't believe I know the answer. Before I quit, I want to thank everyone here for their kindness. I think you all have been very generous to an old man who is obviously in the fourth quarter of his life. I used to play sports, and you're a lot more energetic in the first half than you are in the fourth quarter. But the fourth quarter is the most important of all. And I'd also like to thank all of the ponentes here for their collegiality It's wonderful when you go to a meeting and everyone respects everyone else and everyone communicates with all of their ideas with one another, even if they disagree, and do it with a good spirit. And I've seen this here. So I thank you all for that.
Thank you so much. We have 2 questions. All right. All right. Should we start? The first one. Candidatus or Rickettsia emblemi was able to generate pathology and an antibody response in guinea pigs. Moreover, its capacity to generate protective immunity against Rickettsia rickettsii may modulate the epidemiology and severity of Rocky Mountain spotted fever in areas where both species circulate. Which strategies could be used right now without it being a potential risk for the human population, especially in places like here in Mexico, where it's has been reported only in the West Coast?
So it's a good question, is whether this could get to people or not. We're going to put it in dogs, so it will be put in dogs. So I don't think that people are going to get it. And I will tell you that judging from the number of people with antibodies in the United States, 10% or more of the population in the areas of the country where the ticks carry this, which is a whole lot of people in the United States, it doesn't appear to be a serious pathogen. But I think that it's going to require more than me saying that. Lucas Blanton probably will arrange a study, a human study, where he will infect people with Rickettsia amblyomyces. And this is not so easy. You have to prepare it in a way to where it would pass FDA regulations for safety. So, I mean, he has to use certified cell culture. I mean, he's going to have to do lots and lots of things. Probably preparing this vaccine for the dogs, he will do those things whether they were going to be required for dogs or not. And he's a very clever guy, and I think that he will figure a way to do the study of challenging people. This is with informed consent. You know, you have to explain to the patient exactly what you're going to the subject, exactly what you're going to do, what the possible risks may be, and you have to be sure they understand it. And then they have to sign their name that they agree to do the study, informed consent. And I think this is feasible. I predict that there is a very good odds that he will accomplish this. And then we'll know the answer to the question. How could people get Rickettsia amblyomyces? Well, you know, maybe there would be some ticks feeding on the dogs that were vaccinated, and they would pick it up. And then maybe they would bite people, and the people would get challenged with Rickettsia amblyomyces as well. I mean, that's possible. And maybe they would have a little illness. I think they would actually be immune to Rocky Mountain spotted fever, but have to consider all these things.
Thank you. The next one is, during the symposium, it has been mentioned that Rocky Mountain spotted fever should be considered as a neglected tropical disease by the World Health Organization. In your opinion, added to the research needed in the development of a vaccine, which other focused research areas should we address?
Say again, the last question.
In your opinion?
No, just the last one.
The last one. Which other focused research areas should we address?
So if this question is to what other areas should we address for control of Rocky Mountain spotted fever in Mexico, I think we've already heard those. We heard those yesterday. We heard lots of plans. Vaccination would only be a component of this. I'm not sure that I interpreted the question exactly correctly, but that's my answer.
Thanks, Dave. And, I think I speak for all of us. You've been an inspiration for my entire career. So I'm very grateful to be part of the solution with you. I'm so happy you're on the team. And you brought up another really important point, I think, at the end, is that the development of an effective vaccine is just one tiny part of it. There's enormous complexity in terms of rolling out that vaccine. And, how many dogs do you vaccinate? Where do you vaccinate? When do you vaccinate? So the first part of my question is, considering that Rocky Mountain spotted fever is sylvatic disease, and, based on some of the work that we heard yesterday from Andreas about, the potential for reintroductions, do you think that this is once a vaccine is developed, that this would be something that would have to be repeatedly administered over time to be effective?
I think we'd have to have surveillance, and when your criteria for potential reemergence were met, you'd have to go back out there and probably use vaccine again. I do not believe it would, if it is ever put under control, which you and I optimistically believe that it's worth trying. I think it could come back. It disappeared in La Laguna probably due to a lot of use of DDT by the 1940s and 50s, where it disappeared, then it reappeared. And I think it reappeared because somewhere out there in nature there's a zoonotic cycle that we don't know about. We don't know what tick it is. In Mexico, they know some ticks in the woods that can infect dogs, and the dogs can come in the house. Well, if there's Rickettsia sanguineus in the house, then you can start that cycle there. Actually, the tick that the dogs bring in the house in Mexico can infect people. So it's a bit different situation there, but it has the same principle of there being a zoonotic cycle in nature that's brought into a home.
Yeah, thank you. And this is actually just directed to the audience, and I would encourage you to think about what you can do, because as Dave mentioned, there are things that need to be planned for. If there's anybody in the audience that's good at modeling, think about what contributions you might be able to bring to planning a rollout of an effective vaccine, whether it's 5 years from now or 10 years from now. But it's going to require a lot of individual participation and a lot of different talents. And I think many people in this room have those talents. And it's been a really satisfying to hear the investigators from Mexico talk about the work that they're doing that's going to participate in a solution. So thank you.
Dr. Walker, thank you very much. I remember the first paper I've read about Rocky Mountain spotted fever from is such about acute kidney failure that you wrote.
1975.
Yeah. So you are one of my inspirations to work on Rocky Mountain spotted fever. So You told us that 40 years ago you thought about the development of a vaccine against this horrible disease. So I don't know how long it's going to take to be real, that vaccine. And as Chris told us, maybe here in this room, some of our students want to follow, to pursue that goal. But I have a question for you, but it's kind of a reflection. So thinking as an epidemiologist, I think a good strategy is to target hotspots to be vaccinated. But that is not attractive for the industry, for the pharmaceutical industry to develop that vaccine. So how could we, contribute to be attractive such a vaccine to be developed and to be commercialized for people? Because we know that we have a lot of dogs and there is a growing trend to have pets. So that's a target for the pharmaceutical industry. But don't you think that we need to do something to be more attractive for companies? You are a scientist, but thinking at the population level, what do you think that we need to do to be attractive for this disease?
So I think governments need to recognize that business, commercial entities are not the answer to everything. That the market drives the production of a lot of things that are very useful to society. Capitalism, it works sometimes, but not all the time. And I think at some point the governments need to step in. I believe it's more probable that the Mexican government could set up a vaccine development facility. It would have to be for lots of things, not just for Rocky Mountain spotted fever. And I think this is probably something the whole world should be doing, because they're not going to be embarking on doing, companies are not going to be embarking on doing things that they will not make money for. They are working for their stockholders. They're not working for the public health. And some entity that cares about public health needs to realize that they need to invest in it. And depends on how things go in the next election to whether there's any chance for that or not in the United States.
Yeah, Dave, I agree with you, and I don't want to sound pessimistic, but I don't think there will ever be a commercially produced vaccine for Rocky Mountain spotted fever in dogs. I don't think, I think that's the reality, that the market's not big enough, even though it's desperately needed. But then we have to think outside the box. And I think, like what Dave said, if this vaccine is produced in a different capacity, not as a commercially available vaccine, then there's hope. And I think, especially if it shows efficacy, in some field trials, that might stimulate, work on a governmental level. I think the other thing, and I believe Dave is going to be speaking on this next, but a vaccine that is directed against brown dog ticks, specifically against the tick, the vector is enormously powerful, and in some ways would be more effective than a vaccine against the pathogen, because you're eliminating all the vectors. And I see that actually as being a very commercially attractive vaccine. I think the possibility of a company picking that up and running with it and being able to sell that, because as you heard, Rickettsia sanguineus, or the Rickettsia sanguineus complex, is distributed all over the world. So you would have potentially a global market. The other thing is Rickettsia sanguineus transmits other diseases besides Rickettsia, like Ehrlichia canis, which is far more prevalent in dogs and very debilitating in dogs. So I think we need to come at this from a couple different directions. There's an immediate need for a vaccine against Rickettsia to save lives. But I think the long-term solution, if a vaccine is really going to be tenable, is going to be an anti-Rickettsia sanguineus vaccine. And there's no reason whatsoever not to be working on both simultaneously.
So actually, Jerry McBride and I have intellectual property on patents that are licensed. And so there is some commercial interest in some of these veterinary issues. And Roman has a bunch of vaccines, and Roman has a vaccine. I mean, we just have an idea. And so I think that it's the bar to get over for a veterinary pharmaceutical product is not as difficult as for human. And so I think that that should help out.
Okay. Thank you very much, Dr. Walker, not only for your beautiful and important presentation, your reflections are very important for us. Thank you very much.
Thank you.
El Departamento de Medicina y Ciencias de la Salud, Facultad Interdisciplinaria de Ciencias Biológicas y de la Salud de la Universidad de Sonora, otorgan la presente constancia al Dr. David Walker por impartir su conferencia Perspectivas para una vacuna canina contra la fiebre manchada por Rickettsia rickettsii. ¿Qué tan cerca estamos?
Muchas gracias.
Your key. Thank you. Bueno, les agradecemos que se sienten. Vamos a esperar a que no haya movimientos para continuar. De pronto hay muchos movimientos. Para continuar con la siguiente presentación, que está a cargo del doctor Dave Wagner. El doctor Wagner lo tenemos por segunda vez aquí en este recinto, en este foro, en este simposio. Él es profesor de Ciencias Biológicas y director asociado del Instituto de Patógenos y Microbioma en la Universidad del Norte de Arizona. Su investigación combina los análisis genéticos, genómicos y filogeográficos de última generación, También realiza estudios de campo para entender de mejor modo a los patógenos, a los huéspedes y a los vectores, incluyendo el desarrollo de herramientas novedosas para detectarlos y caracterizarlos. Es un gusto recibir nuevamente al doctor Dave Wagner para que nos comparta su presentación. Muchas gracias.
Buenos días. Lo sientos for giving a talk in English in Mexico. My Espanol is very limited. I can order a cerveza. I can get directions to the baño. And I know if someone yells out, "Hey, flaco," they're talking about me. So I have tremendous respect for so many of my colleagues that do science and write papers in their second or third languages. It's huge. I work internationally, and I'm tremendously impressed by people that do that. So you have my respect. I'm happy to be here. I'm so happy that Gerardo and Chris extended the invitation. I am new to the Rocky Mountain Spotted Fever field. I've been working on it for about a year. I haven't even published my first paper yet. That's my task for next week, is to get that paper out. And so I've come into a number of different new scientific communities over the years, and some of them are friendly and some are not. This one is very friendly, and I appreciate that everyone's so open, and I think everyone recognizes what a huge problem it is. And as Chris said, we kind of need all hands on deck to solve this huge problem. So what I'll be talking about today are anti-tick vaccines and what I think are the path forward for these anti-tick vaccines. And this is complementary, of course, to the anti-Rickettsia vaccines that Dr. Ganta and Walker just talked about it. And I'm pleased to be following them and honored. And so I'll focus on a couple things here. So robust targets. So what I mean by that are targets. So we have this globally distributed tick group, right? It's probably multiple species, but they're all important. And so we want to develop vaccines that are robust against all those diverse populations, if we can do that. Bivalent. So what I'm talking about here is a proposal to hit the tick in two different ways. Directly with tick proteins, and there's been a tremendous amount of work on that already. And then also indirectly by targeting these required bacteria that live inside the ticks. They're endosymbionts that are crucial for their survival. And I have rhipicephalus here because although I'm new to this field, I've been working on other rhipicephalus ticks for a long time. And so we're looking at anti-tick vaccines for multiple rhipicephalus species. Okay, so research in my laboratory, I've been working on plague the longest, and being here and hearing more about the disease makes me think a lot about plague. Rocky Mountain Spotted Fever and plague are both very acute, so you have to have rapid diagnosis and followed by treatment. The treatments are even the same. I've had plague and I took doxycycline to cure that infection. You know, even the antibiotics are the same. But you have to have that rapid diagnosis and treatment. They disproportionately affect poor people. Most of the human plague cases in the world are in Madagascar and rural areas, very, very poor people. And I've been working there for about 20 years. And they're vector-borne diseases. Now, one of the things about plague is that it's really hard. You couldn't go vaccinate the host species against vectors for plague because it's a black rat and it's everywhere. And so that's kind of hopeless there. But it's not hopeless with these rhipicephalus species because we know what the host species are, or the most important ones. I think we still don't know some of the reservoir hosts, and we can treat those with vaccines. And so I think it's an approach we need to try. Okay, so I'll talk about our work on Rocky Mountain spotted fever and tie that into the work we've been doing on cattle fever, which is an economically important disease of cattle that is vectored by closely related ticks, Rhiphocephalus microplus and annulatus. And my group has been working there for 15 years almost. And we do all kinds of stuff. We go out in the field and collect vectors. We take it back to the lab and do microbiology, including at this in the US, the select agent level. And we do a lot of work with genetics and genomics, including whole genome sequencing we like to do that for high resolution genotyping, especially in a monomorphic species. I would say we still don't know much about Rickettsia rickettsii in terms of its genome because there's so few whole genome sequences available, but it looks to be pretty monomorphic. So then you want to look at the whole genome level. And one of the ways that we do that in things like Rickettsia, where it's hard to get a whole genome sequence, or something like leptospirosis, very hard to isolate and then get a whole genome sequence, is we do these whole genome enrichments. And I'll talk a little bit about that and how we're proposing to use those to develop vaccine targets. Okay, and so ideally, like I said, you can take vectors. We go out in the field every year and collect plague-infected fleas and then isolate Yersinia pestis from them. But you can't always do that. So we do a lot of work with DNA. We have a saying in our lab, in DNA we trust. So that's where we put our effort. And so vectors are great because you can easily collect fleas, in this case, fleas that transmit plague or ticks. You can easily go out and collect them. And then if you extract DNA from them, from the whole ticks, then you've got the tick DNA, you've got the vector's microbiota, so anything that was in or on those, and then any pathogens that are in there. You have all the DNA in that single DNA extract that you can work with, and that's what my group has been doing. So I think, these vaccines, either against the pathogen or the tick, are ways out, but there's other work we can do when it comes to molecular epi and better understanding this disease. And so I'll talk first about some tools my team has developed or modified over the last year to study Rocky Mountain spotted fever. Okay, so, lots of us in this room use qPCR. So we use qPCR in 384 well format to screen for Rickettsia, Bacilli, and Rhiphocephali, because this one these two get confused. And so we've recently revamped some assays there to tell those apart. And the work that got me into this is collaborative work with the CDC rickettsial zoonosis branch. And Maureen talked about two tribal areas yesterday, Tribe 1 and Tribe 2. And so we were working in with Tribe 1, going down and collecting ticks with the CDC, and then taking them back to our laboratory, extracting DNA and doing a variety of analyses. And so in 2022, we extracted DNA from over 3,000 ticks. And of those, about 98% assigned to the temperate lineage. We heard some great talks about the diversity of this tick complex yesterday. And so most of these were temperate, but the tropical was also there as well. And these were mostly questing ticks collected near homes. And so we tested them, and about 1.5% of the ticks that we collected were positive for Rickettsia. And then a little more were positive for Bacilli, and no Rhiphocephali detected. So, okay, so PCR, great tool that lots of people use. The next tool that we use is something we call amplicon sequencing. So whole genome sequencing is cheap now, but if you think about a sequencer, you can either put whole genomes on there, or you can parse that out into a bunch of different smaller amplicons, like 16S amplicon sequencing would be one idea. We just do that with hundreds of different targets at a time. And so that allows us to get amplicons, so we get the sequences, So we can do very inexpensive multiplex sequencing at a number of different genomic locations across a bunch of different samples. And so remember, in that DNA extract from ticks, we've got the tick DNA, we've got the pathogen DNA if it's there, we've got the microbiome, if everything else that's in there. And so we can design these AMP-seq targets to detect whatever we want. Well, they can be vector targets, they can be pathogen targets, they can be the endosymbiont. And so we use this tool in this study system to just look at the R. sanguineus using, typical genotyping, loci 12S, 16S. And what we found was kind of interesting. So here's a phylogeny of the sanguineus, and we saw one of these, or whatever this complex is, sensulato. And so what we found, okay, so here's the tropical lineage, here's the temperate lineage, and then it's a whole mess in between, right? And so from that single study site in central Arizona, we had ticks assigned to both the tropical and temperate lineage, and then multiple lineages within the temperate, suggesting multiple introductions, right? So Janet talked yesterday about how quickly these ticks can move around. I mean, I've taken my dog across the Mexican border and back, right? People can move these things around, move the ticks, and possibly move the pathogens, no doubt move the pathogen as well. And so in just this one small study area, we found a great diversity of ticks. So that tells us that the ticks are moving around quite a bit. There have been multiple introductions. And then if you just look at sequences from ticks from North America and northern Mexico here in blue, they're also widely distributed. But one of the things you'll see, and this is the paper I need to work on when I get back next week. This is a collaboration with the CDC, Janet's lab, and Andres down here. One of the things you'll see, though, with some of these typical approaches we use to look at lineages of ticks is they all look the same. These are a bunch of U.S. States, and there's not diversity in there. And so what we would propose in the future for sanguineus is to develop a much more high-resolution genotyping system for this microsatellites. And I'll show you the utility of that when I talk about the cattle fever ticks. Okay, we've also used the same AMP-seq approach to look at for known and discover new acaricide-resistant mutations. So mutations associated with the synthetic pyrethroids, fipronil, and then some of these other ones as well. And you can do that because if you go into another species and you know that there's a mutation that's associated with resistance there, you can just design it in the homolog of your target species and then screen for that. You'll get the mutation. What the mutation means is a different thing. So we did a dermacenter variabilis study years ago, and that was vets sending us ticks. And so in the process, they also sent us some sanguineus that we had extracted DNA from, but just left in the freezer because we weren't working on sanguineus at the time. So we went back and grabbed 94 of those ticks from across the US, and then used this to assign the ticks to one of these lineages, like I just said, and then also screen for acaricide resistance. I mean, one of the things we found, and there's another paper that came out this year that showed a very similar pattern, is that the tropical and the temperate lineages, tropical in white, temperate in black, and then locations where they're both found in gray, they're both distributed across the US. Okay, so I think calling them temperate, tropical, I'm not sure what that means anymore because it sort of implies there's a temperature impact there. Maybe there is, maybe there isn't. I'm not an expert on this tick, but we find these two main groups throughout. And what was interesting is we found this mutation that has been associated with synthetic pyrethroid resistance in this same tick. We found that that was common in the tropical lineage in the US, so anywhere where you have these triangles. And we also found that same SNP was present but rare at the Arizona site. There it was in the tropical, or excuse me, it was in the temperate lineage. So we find that SNP in both of those, suggesting that there's been development of pyrethroid resistance widespread in the US. And then we also looked for some of these other mutations associated with fipronil and found those, but there's gene duplications there. We don't really know what that means until, because these are just potential these are genotypes. We don't know what the phenotypes are. So the next study, or one of the future studies we need to do, is get ticks that have been tested for acaricide resistance. Larval packet tests is how you do this. And then genotype those so we can correlate the genotype with the phenotype. And that's really powerful when you have that, because then you don't have to do the phenotypic assays. You just do the genotypic assays. And I'll show that in the cattle fever ticks. And something that's happening right now, I'm waiting for my group to email me the results of this. So we're doing genome-wide DNA capture and enrichment of Rickettsia, and then it's the Coxiella-like endosymbiont of Rhiphocephalus sanguineus. Okay, so when you see Science or Nature papers and they talk about this disease was found 5,000 years ago and this is what it is, or they genotype things from a couple thousand years ago, this is what they do, right? So this is a technique that came out of ancient DNA studies, and this is actually how I got into it. We generated the first plague genome from the first plague pandemic from a 1,500-year-old skeleton. But, you know, I had this realization that, wow, we can be using these for contemporary samples, right? So let's start applying this to some of these contemporary samples that we have in our collection. And so it's pretty straightforward. Well, it's not pretty straightforward. It's hard to do, but the logic is pretty straightforward. So you have that complex DNA extract. I talked about how you get lots of different organisms when you extract DNA from a whole tick. In the case of ancient DNA from humans, it's usually something like teeth, but we've done it from air filters. So these complex samples, you extract DNA from them, and it's full of all kinds of background DNA that's not probably of interest to you. And so then you need to pull the needle out of the haystack. And the way you do that is you have RNA probes that are complementary to the target genome. They capture the target DNA, you pull it away, and then there's a lot of details behind this, but then you generate whole genome sequences based upon just that pulled away and targeted target DNA. And so then you can do whole genome phylogenetic comparisons, which facilitates high resolution genotyping using the entire genome. And then you can also look at comparative gene content analysis. And so that's pretty important when we're going to look at these tick endosymbionts, because they can't be cultured, right? And so if we want robust genomic information from them, we're going to get that via these capture and enrichment. Okay, so this is what we've done in the last year on Rocky Mountain spotted fever. A lot of this comes directly out of our 15-year-old work we've been doing over the last 15 years on cattle fever ticks. So there, things are a little more robust, but they're very complementary to each other. Okay, so in cattle fever ticks, I mentioned that for sanguineus, we think we want to develop a microsatellite genotyping system in the future. And this has been really powerful in Rhiphocephalus microplus. So for those of you who don't know, microplus is widely distributed in Mexico, and the U.S. has had this concerted effort for decades to try and keep it out of the U.S. And it keeps coming in Mexico, in Texas. And so there's a huge emphasis there to understand these new tick infestations that happen along the U.S.-Mexico border. Okay, and so the power of a database, think about a human DNA database. The power of that is you can genotype someone, but that doesn't really mean anything unless you have a database to compare that genotype against, right? You want to look for a match, or you want to know something about who that individual is related to. So the power of using this over 15 years is we've got over 8,000 individual ticks genotyped in this system. So when there's a new tick infestation of cattle fever ticks in Mexico, we genotype them, and then we compare them to that database and can figure out where they likely came from, if it's been moved around. I think this would be really useful in sanguineus to understand local population dynamics of the ticks. And so just think of them as DNA fingerprints. And there's all sorts of things you can do once you have these data. But here's a recent example. So there was a cow that was brought in from Mexico that was infested, that wasn't detected. The tick infestation spread to other cattle, and then those other cattle, this yellow group here, were spread all throughout Texas, way outside the quarantine zone where they're not supposed to be. And so when you have these robust tools, you can identify these types of events and understand how the ticks are moving around, which can be really invaluable. We've been using AMP-seq to screen for pathogens. So we screen for the variety of pathogens that are transmitted by microplus. For example, Roman mentioned Anaplasma marginale, and it's very widespread in Mexico in these Rhiphocephalus ticks. Again, we're doing all this from just tick DNA extracts. And so moving on towards tools we'll use for vaccines. So remember, so all ticks, it appears that all hard ticks at least have obligate endosymbionts. So what does that mean? That means, so blood is a very poor, nutrient-rich source of food, right? And so they have these bacterial endosymbionts that have evolved inside the ticks. They're passed along from generation to generation. Those endosymbionts can no longer live on their own by themselves. They're in this symbiotic relationship with the tick. They provide the tick with things like amino acids or B vitamins or other things that the tick needs to survive. So it's a symbiotic system. One can't exist without the other. So we're trying to study those. And the way we study those is we do this genome-wide DNA capture and enrichment. We're doing it with the parasites as well. I'm not going to talk about that today because it's not relevant, but we've in one experiment, I don't know, quadrupled the number of genome sequences that are going to be available for these Babesias because it's really hard to get isolates. You can do it, but it's hard. But we've been doing it also for the Coxiella-like endosymbiont of microplus of the clerm. And so when we do that and we map it back to a reference genome, we find we cover almost the entire genome. We would cover the whole thing, but we don't put the entire genome in our enrichment system. We ignore things like 16S or other things that would be found in other organisms that might be inside those ticks. And so what does this mean? That means that we can then do comparative genomics to look at gene content in these endosymbionts across different strains of these endosymbionts and identify the genes that are conserved. Some are just found in single ticks or endosymbionts in single ticks, but a number are conserved, and that's important. I'll explain why conservation is important here when I get to the anti-tick targets for vaccines. But we have to have targets that are conserved across all the species or all the individuals of a species that we're looking at. And so this is a way to do that for the endosymbiont. Okay, and then just last thing on microplus, what we've done there is what we want to do on sanguineus is we've gone in, at least for the synthetic pyrethroids, we were able to take phenotypic data and genotypic data and determine that the presence of any two SNPs correlates with resistance to these synthetic pyrethroids. And that's great because what we do for the USDA, we've essentially been on retainer for the last 10 years. They have a tick outbreak. They send us the tick DNA extracts. We do the microsatellite genotyping, and then we tell them if the populations are likely resistant to pyrethroids or not. And that's important because it determines how you treat those. I haven't heard anybody talk about resistance in sanguineus at this meeting. I find it hard to believe that there isn't resistance in sanguineus populations in Mexico. Maybe that's true. Maybe they're not being treated enough. But what we found in microplus is we watched it increase, right? So resistance in microplus in Mexico is very widespread. And the infestations that are making it into the US now are increasingly resistant. So we've watched that increase. Our study site in Arizona, we found just a couple of ticks that are resistant, have the resistance genotype. I find that concerning because that's how it starts, right? It starts with just a couple. Okay, and so as I was saying, resistance genotypes are widespread in Mexico, and we find that in the ticks that are imported into the US. And I just want to point this out because the main tool we use to control microplus is, and annulatus, right, would be acaricides. And the scientific literature, there's so much evidence of this. I mean, just think of malaria, right? We were so lucky in the US that we eradicated malaria while DDT still worked. DDT doesn't work for a lot of Anopheles mosquitoes these days, okay? So this game that we play with vectors is an evolutionary arms race that they're gonna win. If we're not really good about it, they inevitably win this arms race, okay? So it is time to start looking for other tools. And we think an appropriate tool is an anti-tick vector. And we started exploring this in microplus a number of years ago, and we are moving the same approaches over to sanguineous. Okay, so anti-vector or transmission blocking vaccines. Okay, so simple concept or the basic concepts of this are that you vaccinate the host with vector proteins. And so for microplus, that's cattle. For sanguineous, that would be dogs. The host creates specific antibodies against those proteins. Those antibodies are taken up during the blood meal. They bind to targets inside the tick and negatively impact or kill the tick, blocking disease transmission. And this works because these IgG antibodies can cross the tick midgut, enter the hemolymph. They can persist through life stages and reach various conditions. And they still work when they're inside the tick. So you're using the host immune system to attack the tick. And this is not new, okay? This is not new. There's been over 55 tick proteins tested in animals. And so this has been a very active area of research across different tick species. And there are significant benefits, and Chris just talked about this. Thanks for setting me up there, Chris. This can control the ticks with less risk for other species or the environment, right? We don't want to just be spraying acaricides everywhere. Potentially lower costs. It protects the host against all pathogens transmitted by the tick vector. Okay, so you're taking out the vector. Hopefully you're negatively impacting transmission of all the things that it can transmit. And I think this is important. People are crazy about their dogs, right? I mean, I asked Andres, why don't we just kill these street dogs? I don't mean to be harsh, but why don't we just kill these street dogs? People don't want to do that, right? And these are street dogs. People are nuts about their dogs. And so if you could come up with an effective vaccine that kept ticks from attaching to your dog, I think there would be commercial interest. And I think there would be the funding to drive progress forward on that. So I think that's a positive to this approach. Okay, but I started at the beginning saying that we need to start this process. Dr. Walker and I were talking about this, and he's been thinking about this for a long time, me not so much. But you have to back up and start with conserved targets. Okay, what do I mean by that? So you want to have targets that are conserved across every representative, ideally, of that species or species complex that you're targeting, right? If you're vaccinating with these proteins and there's amino acid variation, potentially the immune system is going to react differently. it encounters a tick that has a different variant of that same protein, the antibodies that were raised by the vaccination may not work against that tick. And so one of the first steps you have to do is find conserved targets. So some of you may have heard of Tick Guard or some of these other anti-tick vaccines that I think Gavic is used here in Mexico. Some of these other ones are used here in Mexico. And all these are based on one full-length protein, this BM86. And that BM86 comes from different populations depending on which vaccine it is, but always one population, okay? So the first one, this Tick Guard that was used in the US, was based on a single Rhiphocephalus microplus from Australia. It was the first commercialized anti-tick vaccine. And what they found in Australia is that it was useful in some Australian herds, but to the point where it wasn't predictable and they no longer use it there anymore. In the Americas, the efficacy was 0 up to 90%. And that depended on the population. And it was concluded that that's probably due to antigenic variation within the key epitopes or the key sections of the proteins that you're vaccinating with that the immune system is reacting to. Okay, and so we decided to look at this. There is something called the Cattle Tick Vaccine Consortium. They came up with a priority list of 14 anti-tick vaccine targets about 7 years ago. And this included what we would think of as traditional antigen targets, so things like tick salivary gland proteins that the host immune system probably does get exposed to when ticks are feeding on it, but also what we call concealed antigens that the bovine immune system normally would not encounter because they're inside the tick body. So things in the midgut and the hemolymph. And so we decided to screen these 14 targets across 190 diverse microplus using amplicon sequencing. So in other words, we went into the genes that encode those different proteins that are being considered as vaccine targets. We looked at variation in the genetic code and then translated that to possible variation in the amino acids to look at protein variation. So we did this from DNA. And what we found was an explanation for why BM86 vaccines work in some places, but they don't work in other places. So here's the 14 different proteins, and each of these bars is how much variation, amino acid variation there is in those different proteins. And one of the ones with the most variation is BM86. Some of these others are more conserved, and we think those are good anti-tick vaccine targets for both sanguineous and also microplus. And down here, you can just see the variation. Here's BM86, and these red highlights are areas where there's a lot of amino acid variation. So there's quite a bit of variation there. And so that would not be a good target. It's not going to work across all your microplus populations. And so you want something that's going to be more conserved, like these ones over here, where there's very little variation. Okay, so we think moving forward with some of these already identified conserved anti-tick targets is the way to go for sanguineous. Of course, we'd want to look at variation within sanguineous the same way that we looked at variation within microplus. And then we also, as I mentioned, we want to target these obligate Coxiella-like endosymbionts as novel vaccine targets. So attack the tick in multiple ways. Why do we want to do that? So we want to combine multiple Coxiella-like endosymbiont targets with multiple tick targets. That way you're attacking the ticks both directly and indirectly. And that's going to reduce the likelihood of vaccine resistance or escape. Think about antibiotic combination therapy, right? So when you give two different antibiotics that attack the pathogen in two different ways, much less likely that resistance is going to develop. And so that's what we're thinking about with these different types of targets. And then possibly could be combined with anti-pathogen targets I came in here naive thinking we were talking about single antigens for the anti-pathogen targets, so maybe not. Maybe we vaccinate at the same time, though, with 2 different vaccines. Okay, so I think this would work because these cocciole-like endosymbionts are ubiquitous in Rhiphocephalus ticks. So here's a bunch of tick endosymbionts in Rhiphocephalus and other species. And they're the dominant features of their microbiome. So if you do 16S analyses on these ticks, they're loaded with these endosymbionts. It makes sense. They need them to survive. And when we screen ticks, we find that they're present in all the sanguineous and microplus we screen. That's good. You want your vaccine targets to be present, or what you're trying to target with the vaccine to be present. This tells us they're good to go after. So as I mentioned, these cocciole-like endosymbionts are obligate endosymbionts of Rhiphocephalus ticks, and they provide the ticks with nutrients they can't get otherwise. Okay, so there's been these experimental studies where they experimentally remove these cocciole-like endosymbionts, and it negatively impacts the ticks. Now, you're not going to go out and treat ticks in the wild with antibiotics. That's not practical. And also, you're not just taking out the cocciole-like endosymbiont, you're taking out everything else in the tick. So it's not clear what's happening there, but it does show good promise for attacking the CLEs and then that negatively impacting the ticks. Okay, so how do you identify good CLE-based vaccine targets? Well, the first thing we would propose to do is identify the core genome, so the genes that are conserved in all genomes. That's really important. So you want a target that's conserved across all the tick species, and we would propose to do that with genome enrichment. And then we would prioritize core genes that are homologs of Coxiella burnetii. Take advantage of the work that's been done on Q fever to develop vaccine targets there, because Coxiella burnetii is closely related to these Coxiella-like endosymbionts. So let's not reinvent the wheel, and then focus on proteins that are on the cell surface, so you know that the antibodies can attack them. And it holds promise to identify proteins that are conserved across tick CLE proteins, or at least homologs. So maybe there's potential targets out there that would work across multiple ticks. That remains to be seen. This is, these are ideas. We have funding proposals submitted to move this forward on both species. Okay, so what's our approach? The last slide here. What we would propose for an anti-sanguineous vaccine. First, the tick proteins, I would say, are well developed in other species. We would want to screen those for conservation, and I'll talk about that. But first, we would generate multiple endosymbiont genomes from globally diverse sanguineous. Remember, this is a very diverse complex, and if we want something, a vaccine that's going to work globally, that's going to increase the commercial impact of that vaccine. We want to start by looking at global populations of sanguineous, right? To find something that's conserved everywhere. And we can do that with these capture enrichment techniques. And then we would prioritize tick and the CLERS proteins. We wouldn't do a whole lot of genome enrichment, just enough to define the core genome, and then screen across these diverse population species using amplicon sequencing. So, what would we want from colleagues down here would be diverse populations of sanguineous collected from different locations, so we could screen those potential vaccine targets to make sure they would work down here where we really need them, right? And that's something we'll be reaching out to all of you about in the future. Okay, and then, the kind of standard approaches, we clone and purify the tick and endosymbionts proteins using standard approaches, vaccinate mice to look for the IgG response. And then when we would also vaccinate mice with homogenates from tick tissues that contain these endosymbionts, just to verify that they're there and express. And again, you can't culture these things, so you got to get kind of creative with how you validate these things. And then, you know, in the future, along the lines of what Roman and David are proposing here, is vaccinate dogs with these finalized set of conserved proteins from both the endosymbiont and the dog to look at efficacy and down select to the final set of proteins that you need to work against these and challenge with ticks. Okay, so like I said, I've only been working on Rocky Mountain spotted fever for a year with funding from CDC. All that work has been led by, most of it has been led by Nate Stone in my lab, and we've been working with the Rickettsia branch, which has been great, Janet's group, Kathleen Walker and Andreas. And then the cattle fever work has been going for 15 years. That's led by senior research scientists in my lab, Joe Bush, and all that work has been funded by the USDA. Okay, so I hope that made sense. We think that's the path forward, is to start with conserved targets, especially since this is such a diverse tick complex. Find the most conserved targets, hit it two different ways by going after anti-tick proteins and then anti-endosymbiont proteins. So a 1-2 punch for the tick. So that's our plan for moving forward. I'd love to hear if anybody has insights or questions or suggestions. Thank you.
Thank you, Doctor, for your presentation. We have a few questions. The first one is, considering a number of polymorphisms were identified in our micropules, analyzing among geographic isolates of the same species will be necessary for the design of anti-tick vaccine for each region.
Totally agree. I think that's one of the main things we're saying is we have to start with that, right? We have to start with, here's a set of candidate proteins. Let's screen them all, both tick proteins and endosymbiont. Let's find the ones that are conserved and then start working through from that point to down select to the final set that are used. Absolutely. Because the more conserved it is, the more places this vaccine is going to work, the more commercial interest there is going to be in it, and the more likely it's going to be that it's actually going to roll out and be successful. Yep.
The next question is, do we already know the exact mechanism behind the acaricide resistance? And if this is a topic we should be worried in the future?
Yeah, so in some cases, yes. There's one SNP we know is associated with resistance to synthetic pyrethroids in sanguineus. One of the things we like about our approach is you're not just targeting a single SNP. You actually have these amplicons that can be a couple hundred base pairs long. So you can go into regions that are mutational hotspots in other species and sort of do surveillance for SNPs showing up, right? And so you can find these new mutations that may or may not be associated with resistance. And then you do have to take it back to the phenotypic data. So someone in the lab has to be testing ticks with these different acaricides. You figure out some populations are resistant, others are susceptible. You go in and look at differences in those mutations in those different populations. That's what we did in MicroPlus. We need the phenotypic data for sanguineus. Our partner Guy down in Brazil has done that work on sanguineus, and we'll be sending those ticks. So we're hopeful to do that. So at this point, I would say yes, there's evidence. We know of some mutations associated with resistance to synthetic pyrethroids, and we have to figure out what the other mutations are associated with resistance to other acaricides.
And the last question we have here is, once the vaccine is developed, which interventions could be done to effectively prevent the spread of the disease?
Well, this question came up to David as well. I think it's all hands on deck, right? I mean, with this disease, you got to try everything you can do. Hopefully, an tick vaccine would be something that would be cheap enough that if you're grabbing dogs in some sort of vaccination campaign for rabies, you jab them with rabies, you jab them for anti-tick vaccines, and hopefully you spay and neuter them at the same time. How much that's going to cost, I think, is hard to predict now, but it seems like it could be really important. This is an invasive tick. It doesn't belong here. It's taken over. We should try and control it as best we can. And this is one approach. Is it going to work? I don't know. I hope so. There's promise in the cattle fever vaccines that it works if the protein is conserved, the protein that you're vaccinating with. So I think if we start from that, hopefully moving forward, we'll find something that works.
Thank you, Doctor.
Thanks, Dave. Really elegant work, and I'm so grateful that you're on the team to move forward on this project. I think one question I had was you've got a head start on the cattle fever work, and have you actually rolled it out in Mexico or in the United States, in cattle? I mean, have there been any field trials with the Boophilus vaccine?
Yeah. So all that work on BM86, we didn't do that. Lots of people have done that work. So there are a number of different commercially available vaccines now based on that single protein, and that has been rolled out. And that's why we know that it works in some populations and not others. The question was why, and that's why we went in and looked at the variation in the protein.
Right. So I guess that was my question. How far along are you in, the vaccine approach for cattle fever, using the same strategy that you're using for Rickettsia sanguineus? I mean, how close is that to a field trial if you're targeting the Coxiella and the symbiont?
So revised vaccines, yeah.
Right.
Yeah, so there are vaccines out there. So I mean, this is the other paper to work on when I get home. This is the price of travel. Is to get out that paper where we talk about the variation in those different protein targets, right? And then it's for get that out in the community so people see. There's so many people working on anti-tick targets. And so we don't really have a dog in that race, to be honest with you. We just want something that works really well. So what our data show are which are the most conserved ones across that species. So the plan is to get that out, let other people move that forward. So we're proposing to add the endosymbiont targets to the MicroPlus vaccine and then move that forward within the next couple of years, but waiting on funding.
Okay, great. Thank you.
Dave, excellent talk. Enjoyed. Very molecular heavy. Something that resonates well with me.
Yeah, sorry about that. It's the world I live in. Yeah.
I love it, but that's what I do. Two things. One, there is good reason why BM86 is working. There is good reason why the antigenic variation occurs. That is how the tick is fighting. If you select all those conserved proteins out of those 14 or 16, chances are those don't work. So
maybe. Yeah, maybe. It depends on those.
Unless you're hitting something which is a T cell mediated immunity that is heavily hidden from those proteins.
Right.
That's one thing. So the good news there is that if it is very regional specific, the ticks have highly variable but still conserved in the local areas, then that's strain or region specific vaccine can still target to BM86 homologs. That's one thought that I have. The other thought is that you only looked at Coxiella as endosymbiont, but we do know that there are Rickettsia endosymbionts. There are Ehrlichia and Anaplasma endosymbionts. I don't know whether they are in Perspectivas sanguineus, but the other endosymbionts, of course, endosymbiont is something that ticks are living on. They are like helping each other. That's a great way to do that. And of course, same thing with all the even muscular-borne. We are talking about Wolbachia and other species. So I think that's a great approach, but I was wondering if other endosymbionts are also in the table for consideration.
Yeah, good questions. I think your first one was getting at the idea that there may be antigenic variation driven by vaccination with BM86. I'm not sure that's the case because a lot of the populations that we drew from are not from vaccinated populations. I think it's just a naturally variable protein, but it's something definitely to explore. I get what you're saying there. We think it's best to just shift to another protein altogether or specific conserved peptides within BM86, and we've identified what those are. There's a whole thing. You can do this great thing with AI now to look at protein folding to see what's actually available on the outside of a protein to the immune system. To your point about the endosymbionts, yeah, I mean, we pick Coxiella for rhipicephalus because those are the dominant endosymbionts, and so that's what you want to target. But we've also enriched and looked at the genomes of Rickettsia-like endosymbionts, Ixodes scapularis, for example, we've done that. And then the Francisella-like endosymbionts in Dermacenter, we've enriched those too. So I think the approach moves over. It's just we pick Coxiella because that's what these ticks have. It's their dominant.
Just to add something to that, the endosymbionts are not just helping the ticks. The endosymbionts also help pathogenic bacteria living inside the endosymbionts. We have some very implicating data. We identified several genes of Ehrlichia, which are essential for the Ehrlichia survival in vertebrate hosts. But the same genes are not essential in the tick because our hypothesis is that ticks are providing them through these endosymbionts or other means by which they get the survival.
Another reason to target them.
Yes,
right?
exactly.
Yeah, we think it's a novel approach and hopefully complementary. Yeah. I know I'm standing between you and coffee and snacks.
Creo que ya no hay otra pregunta. Le vamos a entregar su reconocimiento, doctor, para que no hable nada más 3 palabras. More than 3 words. Mi flaco. El Departamento de Medicina y Ciencias de la Salud de la Facultad Interdisciplinaria de Ciencias Biológicas y de la Salud de la Universidad de Sonora le otorga esta constancia por su beautiful presentation. Identificación y validación de un blanco robusto para vacunas anti-rickettsiacephαλus. Muchas gracias, doctor. Gracias. Y nos vamos a ir 10 minutos a descansar, 10 minutos nada más. Gracias.